When we talk about functions, it's also helpful to have pictures in your head of some of the basic functions, so that then from that you can extrapolate some of their basic characteristics before we get into problem solving. So we want to talk about a few of these and some of their characteristics very briefly. The first equation that we have, or the first function that we have, is the constant function y equals c, where c is some constant. So this could be the line y equals 7, y equals negative 2/3, but basically just a straight horizontal line. Its domain is going to be negative infinity to infinity. Its range really only exists as a single value, just whatever c is. Our function isn't going to be increasing or decreasing, and so what we would say is that it's actually constant on negative infinity to infinity. And we could also classify this as an even function, since it's a reflection of itself across the y-axis. Next we have the identity function, y equals x. So a straight line with a slope of 1 and a y-intercept of 0. This is going to have a domain of negative infinity to infinity, a range of negative infinity to infinity. It's going to be increasing for all values of x, since it has that constant slope of positive 1. And we can classify it as an odd function, since every point is reflected across the y-axis and then across the x-axis. The absolute value function, y equals the absolute value of x, is going to have a domain of negative infinity to infinity. Its range is going to have a restriction of 0 to infinity, with 0 included, since it never dips below the x-axis. It's going to be increasing on 0 to infinity and decreasing on negative infinity to 0. Since we have that change from increase to decrease, there's a likelihood that we've got a maximum occurring, and in this case we have both an absolute and a local minimum at x equals 0. So again, this point at 0, 0 is smaller than all of the points, or its function value is smaller than all of the values around it, and it's also the overall smallest function value that this will ever hit. The square function, y equals x squared, will have a domain of negative infinity to infinity. Its range will also have the restriction of 0 to infinity, since it never dips below the x-axis. It will be increasing on 0 to infinity and decreasing on negative infinity to 0. It's going to have both an absolute and local minimum at x equals 0, and it's also an even function, which we forgot to mention with the absolute value function. This would also be an even function, since each of these are reflections across the y-axis. Something that's important to notice in terms of picturing the shape of these graphs is that while these characteristics are all identical between the absolute value and square function, the very specific distance difference in the picture of these two graphs is that the absolute value function hits a sharp corner at the origin, versus the square function has more of a rounded curve. So it's important to be aware of these different distinctions and the shapes of these different graphs. We can also talk about the cube function, y equals x cubed, which always follows this, I don't know what you want to call it, sort of a snake-like pattern, an S sort of pattern. It has an unrestricted domain and an unrestricted range. It will be increasing for all values of x, so for negative infinity to infinity. It's an odd function because, again, all of our points are reflected across the x-axis, or across the y-axis, and then across the x-axis. And this graph has no extrema, but it does have what we refer to as a saddle point at x equals 0. What we refer to as a saddle point is where a function is increasing and sort of levels out, but then just continues increasing on the other side. Or if it went from decreasing to decreasing. Not very important for this course, but an idea for later courses to keep in mind. We have the square root function, which is y equals square root of x. Its domain is from 0 to infinity, with 0 included. Its range is negative infinity to infinity. It's increasing on 0 to infinity. And it has an absolute minimum at x equals 0. What's important to note here is that there's no local minimum. In the other cases, those points have been both absolute and local minimums. Here, what we have is a point that's only an absolute minimum. In order to be a local minimum, there has to be more graph on the other side of that point. So since this minimum at 0 is at an endpoint for that graph, we can only classify it as an absolute minimum. And this would be an example of a function that's neither even nor odd, since it's not a reflection across the y-axis or across y and then x. The cube root function would be the cube root of x, y equals the cube root of x. Its domain is unrestricted. Its range is unrestricted. It's going to be increasing on the interval from negative infinity to infinity. It has no extrema. And in this case, we have another odd function. Points reflected across y and then reflected across x. So these are the initial graphs that you want to start keeping in mind, being able to mentally associate that picture with the equation or with that function written in function notation, so that you have a graphical or a geometric perspective of the problems we're looking to solve. We will be adding more throughout the course of the semester, but this is a good batch to get started off with.